Okay, let's start do a walkthrough of a single sample t-test. And let's start by looking at the formula. So the formula for the single sample t-test is really just a generic formula for pretty much all the t-tests will do, but there's a few slight variations, and we'll look at that what that is. But we will start with a single sample t-test. Here's the formula. Here's what you need. Here's where you need to find each part of the formula. So X bar here is just our sample's mean, and everything else, again, is going to be pretty easy to find, but one of these things will take a little longer than the rest. Mu is just that known value to which we're comparing our sample's mean. N, the number of people we have in our sample. The S stands for our sample standard deviation. Now, keep in mind I'm using the notation for sample statistics. In the population parameters, you would see omega, or not omega, you would see the Greek letters used instead of the English letters like I'm using right now. That is not going to throw off the way you do it, however. So either way, if you get thrown off on the notation or what these things stand for, don't get confused between the Greek parameter letters and the English notation. Just follow the steps. That's the important part. So let's start with an example problem. And it says a researcher measures IQ from 6 students at UAB and wants to know if their IQ is different from the national average of 100. So our first step is going to be here to calculate the standard deviation. The reason why that is our first step is because everything else is we either have or it's easy to find. So we can easily find the average of our sample over here. We already have the known value of 100, and N, again, is just how many people we have, which is going to be 6 people that we see in the problem from here. So the only thing that isn't readily available or already presented to us in the problem is the standard deviation. So really that's where we're going to spend most of our time on a single sample t-test. So just a reminder of the formula for standard deviation, it all starts with variance. So the variance here, this is the formula, this is the same one you've been doing, and the standard deviation is simply just the square root of the variance. So that's what we're eventually trying to get to. So for our sample here, we have our X from the page before, and I'm just going to go through a very broken down step-by-step on how to calculate the standard deviation here, and then plug it back into our formula. So X bar is going to be the average for, let me change my pen color here. X bar is just going to be the average for our sample. So if you get the average for our sample here, the average is going to be 111.5. And I'm going to break it down and write it for each one. I do recommend that you break this down in as small chunks as you can. That will help you avoid making some lining up errors and things like that. So I'm going to subtract the mean from each individual item here, each individual observation in our sample, create a new column which is X minus X bar. So the difference between our sample and the mean of the sample. And again, if we were to add these all up, it'd wind up 0 down here. So that's why we want to square this, just like it says in the formula. We're interested in the difference between our mean and the group mean squared. So if we square all these values, we get this new column. So I need the sum of these for the numerator here. And if I add these all up, the formula over here does need that sum. Apologize for that. This is 793.5. So we're not done yet, obviously. This is just the numerator. So the formula here is going to call for 793.5 divided by n minus 1. And again, we have 6 people, so that turns into 793.5, 6 minus 1. Again, I am breaking this down to every tiny step possible. So when we do this, we get 158.7. We are not done because this is our variance. So we need the square root of this in order to get our standard deviation. So square root of 158.7 is going to wind up being 12.597. And I am not going to be picky on rounding. Round up to however many digits you want, as long as it's not a whole number. Here this would round up to 12.6 if we were to do any rounding, but I wanted to list it out as much as possible. So now that we have the variance, we can move on and fill in the rest, or not the variance, I'm sorry, the standard deviation. We can fill in the rest of the formula here. So we have everything we need now. So t equals 111.5 minus 100. Again, we knew this because this was IQ's national average. We already calculated the mean for our sample earlier, so we have that easy. We just got the standard deviation, and if we did round it up, it'd be, again, 12.6, but I'm going to write out the full thing divided by how many people we have in there. So hopefully you can see where we got everything from. We'll break this down. So what we have is t equals 2.24. And we're not done quite yet, obviously. So we need to go to table E6 to find the critical value for t. And we are using a two-tailed test here. Let me change colors once more. Or better yet, a highlighter. We're using two-tailed test here. And the reason why is because my original question was to see if there's a difference between my sample the national average. Just a difference. Doesn't matter whether my difference is larger or smaller. My sample is larger or smaller, I don't care, just look for a difference. So then I'm looking specifically for this column here, the significance level 0.05. So unless otherwise specified, we're going to use 0.05. So the last thing I need to know is my degrees of freedom, abbreviated here DF. So simply for the degrees of freedom, it is going to be n minus 1, in my case 6 minus 1, so I'm looking for the row where it is 5. So if I were to match those up, I get this for my critical value. So 2.571 is my critical value for t. So just a visual representation of what we're doing. Again, there's that critical value we just looked up. The t that I found is 2.25. I think I rounded that up from earlier. It's 2.24, 2.25. Either way, you're going to have the same result here. Here's a visual representation of what we're doing. We're looking at the t distribution. It's just a normal distribution. That's all it is. So the critical value represents where if we were larger than that critical value, we are in what we know as the rejection region or rejection range. That is, if my t-value I just calculated is larger than the critical value and it falls in this red region here, then I say that I would reject the null hypothesis. But here, my obtained t-value is smaller than the critical value, and it falls outside of that rejection region. So again, I would reject the null hypothesis. So you notice here there are two red regions. There is one down here and one down here, because this is a two-tailed test. Meaning I've got a rejection region or a red region in each tail. So our final decision here is that the t-value that we calculated, our obtained t-value, does not fall in the rejection range. In other words, it's absolute value, and the reason why I say absolute value is because, again, we're just looking at a difference. It doesn't matter whether I'm talking about positive 2.25 or negative 2.25. It's not larger than the critical value of negative 2.571 or positive 2.571. Don't get caught up on the signs. They are really not going to matter with this. But our obtained t-value does not fall in that rejection range because it's smaller than the critical value. So word-wise, we say that we fail to reject the null hypothesis. And here's how we would write that result out. So that is t of degrees of freedom, what we found. And here we're going to say that p is greater than 0.05. We didn't calculate p. That is not something we will pretty much ever be doing in your lab. That's something the program does for you. But here, all you have to say is it's either greater than 0.05 or less than 0.05. Here, because we did not reject the null hypothesis, because our obtained t-value is larger than the critical value, we say that it is larger than 0.05. Now, there's some questions about using a two-tailed test versus a one-tailed test. So, no matter what, the null hypothesis, or HO, H sub 0, it's always essentially that the difference between the sample and the known average, or two samples, no matter what t-test we're talking about, the null hypothesis, it's pretty much that the difference is always 0. So in this specific example, there's no difference between my sample, IQ, and the national average. And we saw that our research question is going to drive and give an indication as to whether we are doing a two-tailed or a one-tailed test. So you notice in the question, if it says, research wants to know, that's my research question, that's my goal, and that's going to drive what my alternate hypothesis, or H sub 1, is. And I need to use those clues to tell whether I'm doing a two-tailed or one-tailed test. So if you're looking at this, a two-tailed test is just going to say, is there a difference? And this is what we saw in this practice problem. The researcher wants to know if there's a difference between his or her obtained sample and the national average. Do not care if my sample is larger or smaller than the national average, just want to know if it's different. So that's a two-tailed test. Do not care about direction. Now, a one-tailed test, or language that lends to a one-tailed test, are all going to imply some sort of direction. So you really need to be focusing on the words greater than or less than, more, fewer, anything that gives indication to a specific direction. Then you're talking about a one-tailed test. So let's see how the results would change for this one single sample t-test if my goal had been a one-tailed test from the beginning. So I would change the wording of my example here. So let's say a researcher measures IQ from 6 students at UAB and wants to know if their IQ is greater than the national average of 100. So the key here is now the directionality says greater than. My wording changes, but it turns out all the calculations stay the same. That's pretty much the important part. The only difference we're going to see is when we're comparing to the critical value. So let's walk through how that is. So let's pretend that this had been a one-tailed test from the beginning. Now I'm looking at a different row. I'm looking at the level of significance for a one-tailed test. Really, again, we're still going for that alpha level of 0.05. And you see all that does is really shift me, all that does is shift me one column over. So I'm no longer looking at this column. I have shifted to looking down towards this column. So my degrees of freedom stays the same. And so if I match this column columns up, my new critical value for t is 2.015. Now, this changes things, because here's that critical value I just found, 2.015. But now that I have a smaller critical value, my rejection region, this red area, is a lot larger. And that's also because I'm no longer splitting it between two tails. I'm only looking at one end of this distribution or another. So I get to put my rejection region all in one tail, so it's a lot larger. Now in this case, my obtained t-value of 2.24, 2.25, it is larger than the critical value. So it falls within the rejection region. And here's how we would write those results. We would say our obtained t-value is larger than the critical value. So our wording is, I reject the null hypothesis at this 0.05 significance level. And again, we would write up the result. The sign has changed for the p-value because with this obtained t-value 2.25, it is now larger than the critical value. So that is a single samples t-test.